Good morning everyone. My name is Hemant Nag. I'm Associate Professor in the Department of ECE, Lindy Institute of Engineering and Technology. As part of Microprocessor and Microcontroller Lab, today I'll discuss the multi-byte addition program. I'll explain the program, then I will demonstrate how the program works using the Microsoft Macro Assembler. As you can see here, so I have written the code of the program here. So let us put the title here, multi-byte addition. So this is an addition between two numbers whose size is of multiple of bytes. Okay, so two numbers, let us say n1 and n2, the size of each is multiple of bytes. So multiple of bytes means some k times a byte, or so both are of equal size, so k times byte. Okay, so such numbers we are going to add, such numbers n1 and n2, two numbers we are going to add. So generally if I look at 8086 can perform 8-bit addition or the 16-bit addition. So if you want to perform any addition higher than 16-bit, I have to either use repeatedly the 8-bit addition or the 16-bit addition. So we will be using the method of repeated addition to perform higher additions. Okay, so this is a common method we generally use in our decimal number system. As an example, I'll put an example here. So 376 plus 251. So if I have a number like this, if I have to perform addition of these two numbers, so what should I do? So I start with the lower position digit. So this is the lower position digit. So add the two the digits in the corresponding position. 6 plus 1 7. Then I will move on to the higher position. 7 plus 5 12. So as the addition sum is greater than the radix, in the case of decimal, radix is 10, radix of 10. So 7 plus 5 is 12, so which is greater than the radix. So the radix is taken as the carry to the next higher position, and the remaining value out of 12, if I take 10 as a radix carry, the remaining part is 2, that will be taken in the corresponding position. Now if you look at the next higher position, I have 3 plus 2 plus 1, so that will lead us to 6. So this is how we perform a larger number addition in the decimal number system. In the similar fashion, I can go on with hexadecimal numbers or the binary numbers which are greater than 8 or 16-bit using 8086. So here the higher size of the numbers are multiple of bytes, because I am choosing the 8-bit as the repeated size of addition. Okay, so as an example, in this program you can see the first line is assume CS code DS data. Here I am specifying that code segment register should make use of the label code which consists of the program, and DS is the data segment register which should make use of the label data which consists of the information of numbers and the result. Okay, so the next line if you look at, so data segment, so this is the declaration of the label data which is defined as a segment. So this is a keyword of the assembler directive. So this is a keyword known as assembler directive. So this defines data as a label to a segment. Now within the segment we start with the 0 offset address. So to set to a new offset address we use org directive. So org stands for origin. Org stands for origin directive. So this sets the new offset address to be 3000H. Okay, so at this new 3000H offset address, I have declared the label number NUM1, which is defining elements in the size of bytes. So db in this context stands for define byte. So the 3000 offset is given the label NUM1, from where the elements are defined in the size of bytes and occupy the successive memory locations. So if you look at here, as we have written something like this, so the A7, the first element, takes the memory 3000, stored in memory 3000, and 3001 has 23, and similarly 3002 has 67, the following one, and 3003 9C, 3004 3005D, 3005 2E, and 3006 EC. This is how successive bytes were stored, and we are taking the first byte as the lower byte of the number 1. So we have to add two numbers. So here I am writing the first number name as NUM1, whose lower byte is given as A7. So we store in memory the lower byte first, and the successive higher bytes are stored in the higher addresses of the memory till the last byte is stored in the highest address that is possible. So this is how we store the first number that I need. So if you have to write this number, we generally write the lower digit towards the right side and the larger digit towards the left side. So this will be read as A7 23 67 9C 5D 2E and EC. Okay. Now this is my first number. I have declared it as NUM1. So this is my number 1. Sorry, NUM1. Now as you look at the next line, ORG 4000, this will set the offset that is from 3006. So this will change for the offset that is currently at 3006 to 4000. So we'll be having the new offset address available as 4000 once we go with ORG 4000, which stands for ORG stands for origin. So at this address we give the label NUM2. So that means 4000H has the label of NUM2, from where we are defining elements in the size of byte by db directive. Then we have the bytes given here, so which are going to occupy successive memory locations. So in 4000 that will be 7C, 4001 that will be BA, 4002 so 4F, 4003 it will be 77, 4004 it will be 3A, 4005. Okay, so that is E6, and 4006 it is 48H. Now if I, as this is the lower byte of the number, okay, which is stored in the first address, that is in the 4000 address, and the largest byte of the number, or the higher byte of the number you can say, is stored at the last address, that is 4006. Now if I had to consider this as a number, we generally take on a paper the numbers with the lower digit at the right and the higher digits are at the left end. So if you look at here, so this will be like 7C, BA, 4F, 77, 3A, E6 and 48. So these are the, this is the number 2 you can say. So these are the two numbers. If I have to manually perform the addition of these, we start with the lower byte. Okay, so we are going to perform byte by byte addition, repeating it from the lower end until we reach the higher byte, highest byte that is available. Okay, so this is the first position. Okay, so we'll be adding the bytes of number 1 and number 2 in the corresponding first position. So as you can see here, we have 7C. Okay, so 7 and C stands for 12. So 12 and 7, 19. But in the case of hexadecimals, we are taking the hexadecimal. So 16 is taken as a carry to the higher digit. So remaining part of the sum, okay, that is 3, is taken as a sum in the corresponding portion. Now this is the carry from the lower 4 bits to the higher 4 bits. So this is called as the auxiliary carry. Auxiliary carry. Okay, so this is the carry from lower 4 bits to the higher 4 bits in the 8-bit addition. So that is why it is called as the auxiliary carry. Now if you look at here, so we'll be now adding A, which is 10, 7 and this auxiliary carry of 1. So this will stand out to be 18, but as it is hexadecimal, the value, the sum value is higher than 16. So 16 is taken as carry to the higher portion as 1, and the left out value, that is out of 18, 16 is taken as carry, so the left out part is 2. So that will be taken as the sum in the corresponding position. So this is the addition that we are intended to do within one instruction of 8086. within the one instruction of 8086 we want to perform 8-bit addition. So this has resulted in a carry that can be used in the next step of 8-bit addition, next 8-bit addition. So we will repeat this for the next 8-bit in the higher position, and the carry that generated from this position will be given to the next higher position, and so on until we complete the last byte addition. So if you look at this number, we have total of 7 bytes. Okay, so 1, 2, 3, 4, 5, 6 and 7. All these 7 bytes, once we complete, we have the total number added, okay, which is number 1 and added with number 2. Okay, I'll now complete the total sum and see the manual result. So you can check the result here. So after performing the repeated addition in each of the position from the first, second to 7th position in the corresponding bytes, we get the final sum as this. So this is the sum, and finally the carry is obtained as 1. Okay, if you look at here, I have circled few of the ones with purple color, indicating that they are the carry from the previous byte addition to the current byte addition. Okay, and there are few carries that I have circled with blue color. Those are the carry from the lower 4 bits to the higher 4 bits of the 8-bit addition. So these are considered as to be auxiliary carry, and this byte to byte carry is considered to be the carry from one 8-bit to the next 8-bit addition. Okay, so this is the expected result. So this is what we are expecting. So this is the expected result if the program works properly. Okay, now this is what we are expecting, but this is a program. I'm still continuing here. So I have just only stored the second number here using this statement. Okay, so the first number and the second number actually stored in this fashion. So the point you have to remember is the lower bytes are stored first with the beginning address, and the higher bytes are occupying the next higher addresses in the memory. But in the mathematical operation, we always keep the lower bytes towards the right and the higher towards the left. So don't get confused. So you have to treat them in a different way to actually make sense of the result. Now the next line, if you look at len equ $minus num2. So what I'm doing is I'm trying to find the number of bytes within each number that I have provided. This is done by equate operation. So EQU stands for equate. So dollar returns the following address that is being currently used. So if you look at here, number 2 ends with 4006. The following address will be the 4007. So this is what is dollar stands for. Now minus num2. num2 is a label defined for defined to indicate 4000 offset. So when I say minus num2, it actually goes by 4000, which is the offset equivalent of the label num2. So which will result, when we subtract this two, which will result in the value 7, which is the number of bytes in each number that we are trying to add. So in the case, in the simple sense, in the multi-byte addition, the k value or the number of bytes which defines the size of each number is obtained here by using this statement. So this gives us the multiple value of the byte size, okay, of the given numbers. Now as we move further, you can see here. Now after this is done, which is defined as len, so now len is actually of value 7. len is of value 7. Now I have org 5000. I am changing my offset address to 5000, okay, using the org directive. Now this is the location of offset where I am going to define a set of bytes to be reserved for my result. So what I did, I am giving the label res at 5000. So that is res is the label given to the offset address 5000, where I am defining bytes. So the elements we are going to take are going to be defined as bytes, but instead of giving the element value, I am going to specify the number of elements and the default value they should consist before we proceed with the program, finally obtaining the actual result. So len plus 1 is the number of bytes I am going to consider from the given offset, and each of these bytes are going to have the default value of 0, which is given in DUP 0. So DUP duplicate. So DUP stands for duplicate. So in another sense, I am trying to take 5000 and I am going to take the value within 5000 as 0, 5001, and that is also 0. I am going to do this for len plus 1 times. For the from 5000 offset, I will be taking len plus 1 time locations, those many bytes, as zeros. So len is, as we come to know, as 7. So this will be 8. So first second. So 5002 takes the 0, 5003 0, 5004 0, 5005 as 0 again, 5006 0, 5007 as 0. So these are total of 8 locations, 8 successive bytes whose value is set as 0. Why do we take 8? The length is 7. If you look at the result here, so whatever the size of the numbers we have taken for addition, an extra carry is going to be generated, so which is taken as the 8th byte. So whenever you look at the result will have always size of number added plus 1 times is the number of bytes we have to consider, plus 1 bytes. Okay, so this is the size of result that we have to consider, which is done in this fashion. Now, and I take the next line as data ends. So previously we have defined the segment whose name is data, and this is the content, whatever we are writing between the declaration of segment and data ends is the content of that segment. So if you take, this is my content, which is only consisting of data, storing the number 1 and number 2 bytes, and taking few locations for our result. Now I have to end this segment by this statement, data ends, the name of the segment followed by ENDS as the keyword. Okay, so until this point we have only stored the data. Now let us go on with the code. Only we have stored data in this segment. Now I have to declare another segment with the name code, where I am going to store the code or the program of the multi-byte addition. So as you can see here, so this is the program that is stored within the new segment by the name of code. So this is declared here. So a code label is given to a segment. So this is the declaration, and this segment ends here. So this is the end point of the segment. The statements in between these two lines are the instructions or the program of the multi-byte addition. Now, as we come to know, the beginning of every segment we have the offset address of 0. To set to a new offset address, we use the org directive. So this will set a offset to 2000 address. So from here on, the instructions that we have written will be converted into machine code by the assembler. So in our example, in our demonstration, we'll be taking Microsoft macro assembler. Okay, so that will convert this instructions into machine code and will be storing from 2000 offset. So we'll be not discussing here how it converts into machine code, but we'll be looking at how these instructions work. So our aim is to perform repeated additions, okay, starting from the lower byte and propagating the carry from the lower byte addition to the higher byte point, which will be used for the next additions. Now if you look at here, so we are taking the first instruction, move AX data with a label start. So this is the point where the code should begin. The code is indicated to begin. Move AX data. So as you know, data is a label given to the segment which consists of the information. So that name is used here, that label is used here. So it will be transformed into the base address of the segment. So this will be transformed into some base address of the segment, which is taken in AX. That is further given to DS register. So DS register will get the base address of data. So it is not directly provided into DS, it is first provided to AX, then AX will provide it to DS in a indirect fashion. Now after this, we are going to declare few pointers to the number 1, number 2 and the result that is being defined in the data segment. So here move SI offset NUM1. As you know, NUM1 is defined in the above statement at 3000 offset. So this 3000 offset is now given to SI by this statement. So offset of NUM1 given to SI. Similarly, DI will get the offset of NUM2, which is 4000. And BP register will get the offset of RES, which is the result. Okay, so BP will get the offset of result, which is 5000. So these are the pointers. So now my program has pointers at 3 different locations: 3000, 4000 and 5000 offsets. Okay, now as we move further, we have to start getting the value that is stored at 3000 and 4000 and add and store it in the 5000 address. Okay, so we already have the information of content stored at 3000 and 4000. But for the first byte addition, as you can see the example previously, for the first byte addition, there is no previously available carry. But for the successive additions, we have some carry available from the previous addition. So what mnemonic of instruction should be used is to be decided. We have 2 instruction mnemonics, ADD and ADC. ADD is simple addition. Okay, so if I take ADD AL comma BL, so it will simply means AL is given the result of AL plus BL, simple addition of the 2 values. Whereas if I write for ADC AL comma BL, so what will happen? AL will get the sum after addition of AL, the current content of AL, with BL plus the carry flag, so which will hold the carry of the previous addition. So this is what we are needed. We need this instruction for the higher additions, not the first byte. Okay, but in a repeated loop, I can't change the instruction for one iteration. So to make that possible, I have to convert ADC to work like ADD for the first addition. So ADC should work like ADD for the first addition, which is possible if carry flag is 0. So for the first addition, the carry flag should remain as 0, whereas for the further additions, the carry from the first addition will propagate to the second and so on. Okay, so this is been done by this instruction. So if you look at here, so CLC stands for clear carry. So for the first time, the carry flag will be 0. Okay, then after that, CX comma move CX comma LEN. So the number of additions I am going to perform depends on the number of bytes that are the size of the numbers number 1 and number 2 that are taken. So LEN is the one where we have counted the number of bytes in the numbers. So CX will be now taken as 7. So CX is 7. Now this part what we are going to have here is the repeated set of instructions to perform the successive addition of the bytes. So in the first instruction, look at here, move AL SI, I get the value from SI to AL. Okay, now observe here, from SI, which is of 3000 currently offset, the value A7 is taken into AL. So AL at this point is A7, and in the next instruction, from the pointer DA, we get the value to BL, so which is actually the location 4000 has 7C, so the BL will have the value of 7C. Now in the next instruction, we perform addition with carry of AL with BL. So if you observe this, so from the manual calculation what we have done, this step is performed. A7 is added with 7C and we get the sum of 2, 3 and a carry of 1, which is taken into carry flag. So this is taken into carry flag. That can be used for the next byte addition. Okay. Now after this, the pointers are the result which is in AL, which is now after the addition, the AL will be changed to 2, 3. It is changed from this to this. This 2, 3 is to be stored in memory, which is pointed by BP pointer. To store that at that point memory location, we use this instruction: move DS colon within bracket BP comma AL. Why were we using DS colon BP is BP as a instruction, as a register when used, okay, we'll use the stack segment register as the default segment register. To change the default segment register to DS, you have to provide the syntax like this. So instead of using SS register as the segment address, it will use the DS register as the segment address, where we have the 5000 offset. So this already has the value of 0, which has been replaced with the 23 value from AL. So this is the way that it will provide the value. After that, SI will be incremented, and DI and BP, all the pointers, the 3 pointers will be updated to the next byte, which is to be used for next addition. So this will change from here to here. So the SI will not going to point here. So this is going to point in this position. Similarly, DI will not point here. So DI will now point to this offset. Similarly, BP will point to 5001, which already had a value 00 that has been put up in the data segment. Now after all the pointers are incremented, we have the instruction loop up. So loop up, what does it do? It will first decrement CX. So CX will be CX minus 1. The current value will be decremented, and that becomes the new value. As we know that CX started with 7. So if you can take CX started with 7. Now this is decremented to 6 now. After it is decremented to 6, it will be checked. So this is the first step in the loop. We will first decrement, then check if CX not equal to 0. So if CX not equal to 0, we go to label given. So go to label given. What is the label given is, here in this context it is up. So I will switch the control from this instruction back to this instruction. So we are going to repeat this set of instructions whenever CX is not 0. Now as you come to this instruction again, the new SI, which is 3001, will provide the data to AL. So new value of AL will be 23, okay, and BL will be provided with the new value, which is BA. Now we'll add the 2 with the carry provided previously. As we can see here, there is a carry from the previous edition. So 23 and BA is added with the carry that is obtained previously, okay, and that will be stored in AL again. Now what will happen? This summation will lead us to the sum DE with no new carry generated. So AL will now change to DE, okay. So this is the new content of AL. Now this will change to DE, okay, after the addition. Now that content of AL is to be stored in the pointed location of BP, that is 5001, in the place of the 0. Now again pointers are incremented. So SI now moves to this point. It points to 3002. DI points to 4004. Similarly, BP points to 5002. Okay. So then again CX is decremented by 1, and that is the operation of loop. If CX not equal to 0, go to label. So CX previously been decremented to 6 is now decremented again, that is 5 now, and it is not 0. So it will go back for the second iteration to the instruction move AL SI. Okay. So in this fashion, we are going to repeat the next byte additions, okay, which will result us in this fashion, will be resulting in the successive bytes B6, 13, 98, 14, 35, and finally we get this result as the carry as 1, final carry. Okay. Now if you had to look at, I'll put the values here. Now I have just provided the results here after every successive addition. Now once the last condition where CX changes from 7 and decrementing successively from 7 to 0, when it reaches 0, all the bytes are taken and the addition is performed, and the results are properly stored in the respective memory locations. The final values of SI, DI and BP are given here, with CX getting to 0. CX is now 0. So that is the point where it will not repeat further these set of instructions. So there will be no further iteration of the loop. That will come to this instruction LA HF. Now why do we need this? though we have stored every sum result from each of the addition process, we are not able to store this one. So to store the final carry that is generated, this carry, I have to make use of these instructions. Now the final carry is in carry flag. So as we know, we have the flag register structure like this. Okay, I will put the structure now. So this is the format of flag register. If you observe here, okay, from in the lower byte, that is 0 bit to 7th bit, we have the carry, parity, auxiliary carry, 0 and sign in their respective bit positions, and this is consisting of information of carry. So I doesn't need all the remaining bits, I only need this bit of carry. So this lower byte of flag register, so this is the lower byte of flag register, is to be obtained to get the information of carry. So this is done by LAHF. This instruction performs that. This is load AH register with the lower byte of, so the lower byte of flag register. Okay, so this simply means that whatever these bits are there, that will be copied into AH. Okay, so AH will have some unknown bits. I am not sure of what are the bits can be, and carry. So these are the 8 bits. I'm unknown of other bits. I'm only interested in this carry bit. Okay, so these are the unknown bits. I don't want their information. So what I have to do after obtaining AH this information, I have to remove whatever the information that these bits carry, and I have to only be left out with the information carried by carry flag. So this can be done by AND operation with 0 and 1. So we have the Boolean relation of x AND with 0 always leads to 0, x AND with 1 always leads to x. So I want to preserve C, so I will AND this bit with 1, and I want to eliminate all the other bits, so I will AND these bits with 0 value. Okay, so I get only carry and the rest of the bits will be 0. Okay, so this is performed by this instruction AND AH comma 0 1. When I say 0 1, this is the 0 1. Okay, if I take these 4 bits, that is 0, these 4 bits as 1. Now after this operation, AH will be left out with only the carry information, okay, which I can store it in memory. So which memory I want to store? In the 5007 memory. Until 5006 I have been provided with the sum results of the successive additions, and 5007 is where I want to store the carry information, which is done in the next instruction given here. It is more like this instruction, that is in the memory location pointed by BP of the segment DS. I am storing AL here, but instead of AL I am going to store AH, which is now carry information. As we know from the manual calculation, the carry information will be obtained as 1 0 1. Okay, so this is how it will be. Now finally, once we have every memory consisting of the result, that is from 5000 to 5007, I will end the program using the breakpoint interrupt int03 and declaring the code segment to end and the code to end in the last statement of end start. So this is how this program works. Now let us move to the assembler and let us practically see this program in action. You can see the code here. I have already written the code. Okay, this is the code which I have made use of the editor in the MASM assembler. Now I will go to the DOS prompt and I will assemble this program by typing the instruction or command, sorry, not instruction, MASM test.asm. So there are no warnings or errors. So I will proceed with the next step of the assembling process, that is linking. Link space test.obj. So my file name is test.asm. Once I assemble it, it will generate a test.object file, that is obj. Now I will use this to link and generate the loadable file which can be provided into memory for verification. Once I proceed with this, once I just keep entering, I go to this point. Now I have to test and verify the program. For this I will use the debug command, debug space test.exe. So once we link, we get the executable file which is to be test. So debug test.exe. So once I give this, we have a prompt of the dash, so where I can check the program's base address and offset address by giving A. Now you can see 0C6B is the base address of segment which consists of code, and offset is 2000. Now to check the code within this segment, you can type U. So if you carefully observe, the instructions there are the ones that we have written in the code segment block. Okay, and if you look at the first instruction, the move AX, 076A, it shows the offset address of, the base address of the data segment to be 076A, where my data is located. Now what I will see, I will try to check the data that is existing there, D space 076A, and I am aware of the offset addresses of the number 1, number 2 and the result, that is 3000, where number 1 is provided. You can see here the bytes in the middle, which is standing from A7 to EC, which are the bytes of my number 1. To check the number 2, D076A colon 4000. This gives the bytes of the second number which are stored in memory. Similarly, if I go with the D076A colon 5000, that will give me zeros. As I have not run the program, it is going to have the default value of zeros. Now to run the program, I give the command G. So this will run the program in a single step with all the statements and ending with the breakpoint interrupt. Now these are the final set of register values and the flag values. But let us look at the interesting part, which is the memory. So D space 076A 5000, where I am supposed to have the result. Now if you observe here, the new result is obtained here, which is taken here. If you check with the calculated value, so this matches with the calculated value, and we can do this program for any size addition, any size addition which is a multiple of bytes. Okay, repeating the iterative steps for n number of times, where n is the number of bytes of the given numbers. Okay, so once I do this, I can quit the debug mode by Q. Okay, so let us return to the program and make the conclusions. As we can see here, the manual calculated value is this, and the obtained value is this, which are the same but taken in the different order. The lower byte is stored at 5000 and the higher byte which is obtained will be at 5007. Now as you can see, this is the one which has 5000, which is having the offset 5000, and this carry which will be at 5007. So with this program, I can perform any sort of multi-byte addition. In the similar fashion, we can go on with multi-byte subtraction. Okay, so only the difference will be in the program we have used ADC to perform the addition with carry. So this is addition with carry, but in the case of subtraction, I have to use SBB, that is subtraction with borrow. Okay, so as the carry propagates from lower to higher bytes, the borrow will propagate from higher bytes to lower bytes. So to make this same program work for subtraction, instead of ADC, I have to use the instruction SBB. So this will change to SBB. So you try your own and see how the result appears and deduce the answer of your own. Thank you.